The average temperature of the universe is 2.7 Kelvin. That is 2.7 degrees above the coldest condition that physics allows to exist. For context, the coldest temperature ever recorded naturally on Earth was measured at the Soviet Vostok station in Antarctica in July of 1983. That reading came to approximately 184 Kelvin. The universe's background temperature is roughly 68 times colder than that record. What humans consider the absolute worst that our planet's climate can produce is, measured against the cosmos, practically mild. But stating a number does not capture the reality. To understand how cold space truly is, and why that coldness is so much stranger and more significant than it first appears, you need to dismantle several assumptions that feel like common sense, but turn out to be fundamentally wrong. Before we begin, if you enjoy space documentaries like this, consider subscribing. We're trying to reach 1,000 subscribers by the end of this month, and your support really helps. Start with the most basic one. Most people, when asked how cold space is, will say something like freezing, or absolute zero, or colder than anything on Earth. These answers feel obvious. Space is dark, space is empty, space is lifeless. Of course it is cold, but that confident answer is wrong. Not slightly wrong, not just imprecise. It is wrong in a way that reveals a deeper misunderstanding of what temperature actually is and what it means for the vacuum between stars. Here is the core problem. When you experience cold, what you are really feeling is heat leaving your body. Step outside on a winter night and the air attacks you. Molecules of nitrogen and oxygen, moving at high speed, slam into your skin billions of times per second. Each collision carries away a tiny fraction of your body heat. Your nerve endings register this energy loss and signal your brain, cold. That sensation is so universal and so deeply wired into human biology that we mistake it for a property of the environment rather than a description of a process. We say the air is cold. We say the water is cold. We say the metal railing is cold. What we really mean is that those substances are conducting heat away from our bodies faster than we can replace it. Cold is not a thing. Cold is the absence of a thing. It is what happens when energy leaves faster than it arrives. This distinction becomes essential when you try to apply the concept of temperature to space itself, because space is not a substance. The vacuum between stars is not filled with cold material pressing against you and draining your warmth. It is filled with almost nothing at all. Remove the air, remove the water, remove every molecule of gas, every particle of dust, every atom of matter for millions of miles in every direction. You are floating in the vacuum of deep space. Nothing touches your skin. No molecules collide with your body. No substance exists to steal your heat through direct contact. So what temperature is it? The honest answer is that the question barely makes sense in the way it is usually asked. Temperature, in the way humans experience it, requires matter. It is a measurement of how fast particles are moving. In a gas, temperature describes the average kinetic energy of molecules bouncing around in random directions. Hotter gas means faster molecules. Cooler gas means slower ones. When those molecules hit your skin, the fast ones transfer more energy than the slow ones. That is why hot air feels hot and cold air feels cold. It is a story about motion and collision at the atomic level. It is a story that requires actors on a stage. In space, the stage is almost completely empty. Consider the numbers. A cubic centimetre of air at sea level on Earth contains roughly 25 billion molecules. That is 25 followed by 18 zeros. Every breath you take pulls in this inconceivable swarm of particles. A cubic centimetre of interstellar space might contain a single atom, maybe less. The density is so extraordinarily low that calling it a gas at all stretches the definition beyond recognition. You could not measure its temperature with any conventional thermometer because there is simply not enough matter present to transfer energy to the instrument in any detectable way. This exposes the first crack in the common understanding. Space is not cold the way a freezer is cold. A freezer is full of cold air, cold molecules, pressing against everything inside and draining heat through direct contact. Space has almost nothing to press against you at all. If you placed a thermometer in deep space, far from any star or planet, it would not read the temperature of space. It would read its own temperature, and that temperature would depend entirely on what radiation the thermometer was absorbing and emitting. The instrument becomes the subject of its own measurement. It tells you about itself, not about the void surrounding it. To understand why this matters, you need to understand how heat actually moves from place to place. There are three mechanisms. The first is conduction. Place your hand on a metal countertop, and heat flows directly from your warmer skin into the cooler metal through physical contact. Molecules in your hand vibrate and transfer that vibration to molecules in the metal. This is why metal feels colder than wood at the same temperature. Metal conducts heat away from your hand more efficiently, and your brain interprets faster energy loss as colder temperature. In space, conduction is essentially irrelevant. There is nothing to touch. No surface presses against you. The second mechanism is convection. Turn on a space heater in a room, and warm air rises toward the ceiling while cool air sinks toward the floor. This circulation distributes heat through the movement of fluid. It is what makes weather possible on Earth, what drives ocean currents, what carries warmth from the equator toward the poles. Convection requires a fluid medium. In space, there is no fluid to circulate, no air to rise or sink, no currents to carry warmth from one region to another. The third mechanism is radiation. Every object with a temperature above absolute zero emits electromagnetic radiation. Your body radiates infrared light right now, invisibly, constantly streaming energy outward in every direction. The sun radiates visible light, ultraviolet light, infrared light, and radiation across a wide swath of the electromagnetic spectrum. This radiation carries energy through empty space without needing any medium to travel through. Unlike conduction and convection, radiation does not need matter. It travels through nothingness, as naturally as sound travels through air, crossing billions of miles of perfect vacuum without losing a single photon to friction or resistance. Radiation is the only mechanism of heat transfer that operates in the vacuum of space, and this single fact changes everything about how temperature works beyond Earth's atmosphere. It means that the thermal experience of any object in space is determined not by what surrounds it, but by what shines on it and what it emits. The void itself contributes nothing. It neither warms nor cools. It simply allows radiation to pass through without interference. Consider an astronaut performing a spacewalk in low Earth orbit. The sun is shining. On the sunlit side of the astronaut's suit, solar radiation pours in at roughly 1,360 watts per square meter. That is approximately the energy equivalent of running a small space heater pressed against every square meter of illuminated surface. The suit heats up. Without active cooling systems, the surface temperature on the sunlit side can climb past 120 degrees Celsius, hot enough to boil water and hot enough to cause severe burns on unprotected skin. Now consider the shadowed side of that same astronaut. The side facing away from the sun receives no direct solar radiation. It radiates its own heat into the void, as infrared photons streaming away into the darkness. With no sunlight coming in and thermal energy constantly leaving, the shadowed surface drops. In the permanent shadow of space, surface temperatures can plunge below 100 degrees Celsius. Some measurements in deep shadow show temperatures approaching negative 170 degrees Celsius, cold enough to turn carbon dioxide into dry ice, cold enough to make steel brittle and crack under stress. This means that a single astronaut floating in orbit experiences a temperature difference of nearly 300 degrees from one side of their body to the other. Not because space has two different temperatures in those two directions. Space has no temperature at all in that region, at least not in the way we normally use the word. The astronaut is simply caught between a powerful radiation source on one side and the absence of any radiation source on the other. The suit responds to radiation, not to the temperature of some surrounding medium, because there is no surrounding medium to speak of. This is what makes the thermal environment of space so alien and so dangerous. On Earth, air acts as a buffer. It smooths out temperature differences. Step from sunlight into shade on a summer afternoon, and the air temperature barely changes, a degree or two at most. The atmosphere acts as an enormous thermal blanket that redistributes energy and softens every extreme. In space, there is no buffer, no mixing, no smoothing, no blanket. Radiation creates savage thermal gradients across distances as small as the width of a human body. The Moon offers one of the most dramatic demonstrations of this principle anywhere in the solar system. The lunar surface has no atmosphere, not a single molecule of protective gas standing between the ground and the void above it. When the sun shines on the Moon's equator during the roughly 2-week-long lunar day, the surface heats to approximately 127 degrees Celsius, hotter than boiling water, hotter than the maximum setting on most household ovens. When that same surface rotates into the 2-week-long lunar night, it cools to approximately negative 173 degrees Celsius, a swing of 300 degrees on the same patch of ground, driven entirely by the presence or absence of sunlight. Earth's surface, protected by its atmosphere, experiences temperature swings of perhaps 50 or 60 degrees between the hottest day and the coldest night in the most extreme desert environments. The Moon's swings are 5 to 6 times more violent, entirely because there is no air to moderate the transition. Even the Moon's temperature extremes tell us only about the lunar surface. They do not tell us the temperature of the space above that surface. A thermometer hovering 1 meter above the sunlit Moon would register a completely different temperature than the ground below it, because the thermometer would be absorbing radiation from the sun directly, and also absorbing infrared radiation emitted upward from the hot ground, while simultaneously radiating its own heat into space. Its reading would depend on its size, its color, its reflectivity, its orientation relative to the sun, and its distance from the surface. Change any one of those properties, and the reading changes entirely. This is why engineers who design spacecraft do not think about the temperature of space. They think about thermal balance. Every spacecraft is simultaneously absorbing radiation from the sun, absorbing radiation reflected off nearby planets and moons, absorbing the faint infrared glow of the cosmic background, and radiating its own thermal energy into the void. The spacecraft's temperature is determined by the balance between energy coming in and energy going out. When those two quantities are equal, the temperature stabilizes. The International Space Station uses enormous radiator arrays, spanning roughly 2,500 square feet, to dump excess heat into space. Without these radiators, the station would overheat from its own electrical systems and the absorbed solar radiation. The 6 crew members aboard generate body heat. The computers generate heat. The lighting generates heat. Every experiment running in the laboratory modules generates heat. All of this thermal energy builds up inside a sealed metal container, floating in a vacuum with no air to carry the heat away. The radiators solve this by facing away from the sun and emitting infrared radiation into the cold void. Simultaneously, shadowed components on the station require electric heaters to prevent them from freezing. Batteries that sit in the station's shadow for extended periods must be kept above certain minimum temperatures or their chemistry stops working. Fuel lines can freeze solid, Optical instruments can crack from thermal contraction. Seals can become brittle and lose integrity. The station exists in a constant battle between roasting and freezing, managed by systems that carefully control which surfaces face the sun and how efficiently heat is rejected into the void. This thermal management challenge reveals something important about the nature of cold in space. The danger is not that space is uniformly frigid. The danger is that space does not care about your temperature at all. It provides no insulation, no buffering, no moderation. Whatever radiation you receive determines whether you bake or freeze, and the transition from one extreme to the other can occur across inches. Shadows in space are not gentle, cool spots like shadows on Earth. They are thermal cliffs. The cold of space is not an assault, it is an abandonment. It is the universe turning its back and leaving you to your own thermal fate. Now consider what this means at larger scales. The spaces between stars. In our region of the Milky Way, the average distance between neighbouring stars is roughly 4 light years. That is approximately 24 trillion miles of vacuum separating one sun from the next. 24 trillion miles where no significant radiation source exists to warm anything. The starlight from distant suns is so diluted by distance that it contributes almost nothing. The inverse square law ensures that radiation intensity drops with the square of the distance from its source. Double your distance from a star, and the radiation hitting you drops to 1/4. Triple the distance, and it drops to 1/9. At 4 light years from the nearest sun, the radiation from that star is so faint it would barely register on the most sensitive instruments ever built. Any object drifting through that interstellar void, a rogue planet ejected from its solar system, a chunk of ice flung outward by a gravitational encounter, even a spacecraft travelling between the stars, would slowly radiate away its own heat, photon by photon, with almost nothing coming in to replace the lost energy. How cold would such an object get? It would cool and cool and cool, shedding thermal energy into the darkness. With each passing year, its temperature would drop past the freezing point of water, past the freezing point of carbon dioxide, past the boiling point of liquid nitrogen, down and down through the temperature scale, toward a floor that it can approach, but never quite reach on its own. That floor is set by the only source of radiation that permeates all of space, everywhere in the universe without exception, the faintest and most ancient light in existence. A glow so dim that no human eye could ever detect it, yet so perfectly uniform that it fills every cubic centimetre of the cosmos. This is the cosmic microwave background radiation. It sets the fundamental temperature floor for the entire universe. Any object left alone in deep space, far from any star, far from any galaxy, shielded from every local radiation source, will eventually cool down until it reaches thermal equilibrium with this background glow. At that point, the object absorbs exactly as much energy from the background radiation as it emits through its own thermal radiation. Its temperature stabilizes, it stops cooling, and the temperature it settles at is approximately 2.7 Kelvin. That is 2.7 degrees above absolute zero, negative 270.45 degrees Celsius, negative 454.81 degrees Fahrenheit. 2.7 Kelvin is the closest thing the universe has to a baseline temperature. It is not truly the temperature of space itself, because space is a vacuum, and vacuums do not possess temperature in the strict thermodynamic sense. It is the temperature that any object will eventually reach if left alone in the void with no other energy sources. It is the equilibrium point, the resting state, the thermal default of the cosmos. To appreciate how extreme this is, consider familiar cryogenic benchmarks. Liquid nitrogen, the substance scientists use to flash freeze biological samples, boils at 77 Kelvin. The cosmic background temperature is roughly 29 times colder than liquid nitrogen. Liquid helium, the coldest commonly used cryogenic fluid on Earth, boils at 4.2 Kelvin. The baseline temperature of the universe is colder even than liquid helium. The only way to reach 2.7 Kelvin in a laboratory is through specialized cryogenic equipment that costs millions of dollars and consumes enormous amounts of energy to maintain. The universe achieves it effortlessly, passively, across almost its entire volume, simply by being empty. Where does this 2.7 Kelvin baseline come from? The answer requires going back to the beginning. Not the beginning of stars or galaxies or solar systems, but the beginning of the universe itself. Roughly 13.8 billion years ago, the universe did not exist. There was no space, no time, no matter, no energy in any form that current physics can describe. Then something happened. The event we call the Big Bang was not an explosion in space. It was an explosion of space. Space itself came into being and immediately began expanding, carrying with it densities and temperatures so extreme that no laboratory on Earth has ever come close to reproducing them. In the first fraction of a second, the entire observable universe occupied a volume smaller than a single atom. The temperature in that primordial instant exceeded 10 trillion degrees, a number so absurd it has no analogue in human experience. Every particle of matter and energy that would eventually become galaxies, stars, planets, oceans, and living organisms was compressed into a seething point of incomprehensible heat. That heat is where the story of cosmic cold begins, because the universe has been cooling ever since. In the first second after the Big Bang, the temperature dropped from trillions of degrees to roughly 10 billion degrees. 10 billion degrees is still hotter than the core of the most massive stars. The universe at 1 second old was a blinding plasma of protons, neutrons, electrons, photons, and neutrinos, all slamming into each other with energies that would vaporize anything in the modern cosmos. Matter and radiation were locked together in a violent embrace. Photons could not travel more than a microscopic distance before colliding with a charged particle and scattering in a random direction. The universe was opaque. Light existed everywhere, but could go nowhere. Every direction was a wall of blazing fog. During the first 3 minutes, the temperature fell below 1 billion degrees, cool enough for protons and neutrons to begin fusing into the lightest atomic nuclei. Hydrogen nuclei formed naturally, since they are just individual protons. Deuterium appeared when protons and neutrons stuck together. Helium nuclei assembled from pairs of protons and pairs of neutrons. This process, called Big Bang nucleosynthesis, lasted only a few minutes. By the time the universe was roughly 20 minutes old, the temperature had dropped too low for nuclear fusion to continue. The window closed, the cosmic forge shut down. The ratio of hydrogen to helium was locked in at approximately 75% hydrogen and 25% helium by mass, a ratio that observations of the oldest stars confirm with striking precision. But the universe was still extraordinarily hot. For hundreds of thousands of years after the Big Bang, temperatures remained above 3,000 degrees, hot enough to keep all matter in a plasma state where electrons roam freely rather than binding to atomic nuclei. Free electrons are phenomenally effective at scattering photons. Every time a photon encountered a free electron, it bounced off in a new direction. Light was trapped, ricocheting through the plasma, like a ball in a pinball machine, with an infinite number of bumpers. The universe was a uniform, glowing, opaque haze, stretching in all directions. Then, approximately 380,000 years after the Big Bang, the universe crossed a critical threshold. The temperature dropped below roughly 3,000 Kelvin. At this point, something remarkable happened. Electrons finally lost enough energy to be captured by atomic nuclei. Protons grabbed electrons and became neutral hydrogen atoms. Helium nuclei captured their own electrons. For the first time in cosmic history, matter became electrically neutral. Physicists call this event recombination. The consequences were immediate and dramatic. Neutral atoms do not scatter photons the way free electrons do. When the electrons disappeared into atoms, the universe suddenly became transparent. The photons that had been trapped for hundreds of thousands of years were released all at once, free to travel in straight lines across the cosmos for the first time. This liberation of light is called the surface of last scattering. It represents the oldest electromagnetic signal the universe will ever produce. Every photon released at that moment has been traveling through space ever since, carrying information about the conditions that existed when the universe was less than 1% of its current age. Those photons are still traveling today. They fill every cubic centimeter of the observable universe. They arrive at Earth from every direction in the sky. But those photons do not arrive in the same form they were released. When they left the surface of last scattering, they were visible light, orange-red photons glowing at roughly 3000 Kelvin, the temperature of a cooling star. If you could have been present at the moment of recombination, the entire sky in every direction would have glowed a deep, dull red. There would have been no darkness anywhere, no shadows, no contrast. Just a uniform dim red glow extending to infinity. Since that moment, the universe has expanded by a factor of roughly 1,100. Space itself has stretched, and every photon traveling through it has been stretched along with it. This stretching increases the wavelength of light. Longer wavelengths mean lower energy. Lower energy means lower temperature. The original visible light photons from recombination have been stretched so severely over billions of years that they now exist as microwaves. Their wavelength has increased from less than a micrometer to over a millimeter. Their effective temperature has dropped from 3000 Kelvin to just 2.725 Kelvin. The entire sky still glows just as it did at recombination, but the glow has been shifted so far into the microwave spectrum that no biological eye in the universe could ever detect it. The discovery of this radiation is one of the great accidental triumphs in the history of science. In 1964, two radio astronomers at Bell Telephone Laboratories in Holmdel, New Jersey, were trying to use a large horn-shaped antenna for satellite communication experiments. Arno Penzias and Robert Wilson were meticulous scientists who wanted their antenna to be as sensitive as possible, which meant eliminating every source of unwanted noise. They calibrated their equipment carefully. They accounted for radio interference from nearby New York City. They pointed the antenna away from known astronomical sources. They even climbed inside the horn and scraped out pigeon droppings, suspecting the birds nesting in the antenna might be contributing thermal noise to their signal. Nothing worked. No matter what they did, a faint, persistent hiss remained in their data. It came from every direction equally. It did not change with the time of day, the season, or when the antenna pointed at different parts of the sky. The noise was perfectly uniform, perfectly constant, and perfectly inexplicable. The signal corresponded to a thermal source at roughly 3.5 Kelvin, just a few degrees above absolute zero. Penzias and Wilson spent months searching for an explanation. They had not been looking for cosmological signals. They were communications engineers trying to build a better antenna. The connection between their mysterious noise and the origin of the universe came from a group of theoretical physicists working just 40 miles away at Princeton University. Robert Dicke, Jim Peebles, and their colleagues had independently predicted that the Big Bang should have left behind a faint thermal radiation filling all of space. They were in the process of building their own antenna to search for this signal when they learned that Penzias and Wilson had already detected it by accident. The persistent hiss in the Bell Labs antenna was not instrument noise. It was not pigeon droppings. It was the remnant heat of the Big Bang itself, the oldest light in the universe, arriving at a radio antenna in New Jersey after a journey spanning nearly the entire history of cosmic time. Penzias and Wilson received the Nobel Prize in Physics in 1978. Over the following decades, increasingly sophisticated instruments refined the measurement. The Cosmic Background Explorer satellite, known as COBE, launched by NASA in 1989, pinned down the background temperature to 2.725 Kelvin with an uncertainty of less than 1,000th of a degree. COBE also detected tiny temperature fluctuations in the background radiation. The radiation was not perfectly uniform. Some directions in the sky were a few hundred thousandths of a degree warmer than average. Others were a few hundred thousandths of a degree cooler. These variations were minuscule, roughly 1 part in 100,000, but they were revolutionary. They represented the primordial density differences in the early universe, the seeds from which all cosmic structure would eventually grow. Regions that were slightly warmer at recombination were also slightly denser. Those denser regions had marginally stronger gravitational pull. Over billions of years, that tiny gravitational advantage would attract surrounding matter, growing denser and denser until galaxies, galaxy clusters, and the entire cosmic web condensed out of the initial smoothness. The Wilkinson Microwave Anisotropy Probe, launched in 2001, mapped the cosmic microwave background with roughly 35 times the angular resolution of COBE, determining the age of the universe to be 13.77 billion years, and establishing that ordinary matter constitutes only about 4.6% of the total energy content of the cosmos. Dark matter accounts for roughly 23%. Dark energy, the mysterious force accelerating cosmic expansion, makes up the remaining 72%. These numbers, extracted from the patterns in ancient microwave radiation, form the foundation of modern cosmology. The European Space Agency's Planck satellite, launched in 2009, refined the measurements further still. Observing the cosmic microwave background at 9 different frequency bands and producing the most detailed images of the early universe ever constructed, Planck refined the age of the universe to 13.798 billion years and confirmed the background temperature at 2.725 Kelvin with unprecedented precision. 3 satellite missions spanning 2 decades transformed the cosmic microwave background from a crude detection into the single most informative observation in all of cosmology. A faint hiss that annoyed 2 radio engineers in 1964 became the Rosetta Stone of the universe. What this means for the temperature of space is that the 2.7 Kelvin baseline is not just a number, it is a fossil, a thermal relic of a moment when the universe was young, hot, and glowing. Every photon in the cosmic microwave background has been travelling since recombination. Each one carries a tiny packet of energy from an era when the cosmos was 3,000 degrees everywhere. Those photons have lost almost all of their energy to the expansion of space. They have been stretched, diluted, cooled from incandescent to microwaves over 13.8 billion years of cosmic evolution. And the cooling is not over. The universe continues to expand. The cosmic microwave background continues to stretch and cool. A universe twice its current size will have a background temperature of roughly 1.4 Kelvin. A universe 10 times larger will glow at just 0.3 Kelvin. The cosmic microwave background is a dying ember, slowly fading toward a darkness that will never quite become absolute, but will approach it over time scales that dwarf the current age of the universe many times over. The cosmic microwave background also sets a fundamental limit on how cold anything in the natural universe can become. No object in space, no matter how isolated or how far removed from any star or galaxy, can cool below 2.7 Kelvin through natural processes. The background radiation bathes everything in a minimum energy input that prevents temperatures from falling further. It simultaneously provides the faint warmth that prevents the universe from reaching absolute zero and defines the extreme cold that characterizes nearly all of cosmic space. It is both the universe's last source of universal warmth and the thermometer that measures the depth of cosmic cold. But the 2.7 Kelvin baseline tells only half the story. The cosmic microwave background describes what happens in the absence of local energy sources. It tells you the temperature of the void. But the universe is not entirely empty. Scattered through the cosmic darkness are objects of extraordinary thermal violence. Stars that burn millions of degrees in their cores, nebulae heated by newborn suns, accretion disks that reach temperatures rivaling the first moments after the Big Bang. Our Sun maintains a surface temperature of approximately 5,500 degrees Celsius. Its core reaches 15 million degrees Celsius. These numbers exist on a completely different scale from the cold that surrounds them, separated from the cosmic baseline by factors of millions. A star is not just warm, it is a sustained thermonuclear explosion, a sphere of plasma held together by gravity and powered by the fusion of hydrogen into helium at pressures and temperatures that have no parallel anywhere else in the natural universe except in the hearts of other stars. The Sun converts roughly 4 million tons of matter into pure energy every second. Not 4 million tons of fuel burned into ash. 4 million tons of mass annihilated, transformed into photons through Einstein's equation relating energy to mass. That energy radiates outward in every direction, crossing 93 million miles of vacuum to reach Earth in about 8 minutes. It warms our planet, it drives our weather, it powers photosynthesis. It sustains every living thing on the surface of this world. And our Sun is not even a particularly impressive star. It is a middle-aged, medium-sized yellow dwarf, unremarkable among the hundreds of billions of stellar furnaces burning throughout the Milky Way. Larger stars burn far hotter. Blue supergiants blaze with surface temperatures exceeding 11,000 degrees Celsius, roughly twice the temperature of the Sun's photosphere. Their cores can reach hundreds of millions of degrees, fusing not just hydrogen, but helium, carbon, oxygen, and progressively heavier elements in nested shells of nuclear fire. The most massive stars known to science, behemoths weighing over 100 times the mass of the Sun, burn through their fuel with such ferocity that their entire lives span only a few million years. Compare that to the Sun's expected 10 billion year lifespan. These stellar giants live fast, burn outrageously hot, and die in cataclysmic explosions that briefly outshine entire galaxies. On the opposite end of the stellar spectrum, red dwarfs burn cool and slow. Their surface temperatures hover around 3,000 degrees Celsius. Dim compared to the Sun, but still thousands of times hotter than the cosmic background. Red dwarfs are the most common type of star in the universe, outnumbering all other stellar varieties combined by an enormous margin. Roughly 70% of all stars in the Milky Way are red dwarfs. They are so dim that not a single red dwarf is visible to the naked eye from Earth, despite being the most numerous objects in the stellar census. They burn their fuel so sparingly that their lifespans extend into the trillions of years, far longer than the current age of the universe. Every red dwarf that has ever ignited is still burning today. Not a single one has yet run out of fuel. Not one has died. When matter falls toward a black hole, it spirals inward through a structure called an accretion disk, a swirling vortex of gas and dust compressed by gravitational forces so intense that the material heats to temperatures rivaling the early universe. The inner regions of accretion disks around stellar mass black holes can reach tens of millions of degrees. Around supermassive black holes, the kind that lurk at the centers of galaxies weighing millions or billions of solar masses, accretion disk temperatures climb into the hundreds of millions of degrees. The most extreme accretion environments found in active galactic nuclei and quasars produce temperatures approaching 1 billion degrees or more. Supernova explosions create momentary thermal extremes that dwarf everything else in the modern cosmos. When a massive star exhausts its nuclear fuel, its core collapses in a fraction of a second. The iron core, roughly the mass of our Sun, compressed into a sphere the size of a city, implodes at speeds approaching 1/4 of the speed of light. The temperature at the collapsing core reaches roughly 100 billion degrees for a brief, violent instant. That is hotter than the interior of any stable star, hotter than any accretion disk, hotter than the universe has been at any point since the first second after the Big Bang. In that instant of core collapse, a dying star briefly recreates conditions that existed when the cosmos was less than 1 second old. The explosion that follows can outshine the combined light of every other star in the host galaxy for weeks, and then it fades. The heat disperses. The expanding remnant cools over thousands of years, eventually merging into the cold interstellar medium. Star formation itself happens in the coldest places inside galaxies. The vast clouds of gas and dust where new stars form, called molecular clouds, sit at temperatures of just 10 to 20 Kelvin, barely above the cosmic background. Star formation requires this extreme cold because only cold gas can collapse under its own gravity without thermal pressure blowing it apart. The process is paradoxical and beautiful. The coldest places inside galaxies are precisely where the hottest objects are being born. Stars emerge from darkness, and the darkness is essential to their creation. All of these thermal exceptions, from the hottest accretion disk to the coldest red dwarf, from supernova to planetary surfaces, share one critical characteristic. They are vanishingly small compared to the space between them. This is the fact that transforms the temperature question from a matter of physics into something approaching an existential reckoning. The hot objects are real. They are spectacular. They are powerful, but they are tiny. Incomprehensibly, laughably, terrifyingly tiny when measured against the void that contains them. Consider the Sun. It is large by human standards. Its diameter spans roughly 865,000 miles. It dominates our local environment so thoroughly that its gravity holds planets in orbit billions of miles away. But the nearest star, Proxima Centauri, sits 4.25 light-years away. That is roughly 25 trillion miles. If you shrank the Sun to the size of a ping-pong ball, Proxima Centauri would be another ping-pong ball sitting approximately 720 miles away. Between those two tiny spheres lies nothing. 720 miles of empty space. Two specks of warmth separated by a wasteland that dwarfs them by a factor of roughly 30 million. You could line up 30 million suns between our star and its nearest neighbour and still have room left over. Each one of those suns would be a screaming furnace of nuclear fire, and the gaps between them would still be cold, dark, and empty. Scale this up to the galaxy, and the proportions become even more extreme. The Milky Way contains an estimated 200 to 400 billion stars. That sounds like an enormous number until you consider the volume they occupy. The galaxy spans roughly 100,000 light-years across and 1,000 light-years thick. Divide the total volume by the number of stars, and each star commands on average a private empire of roughly 20 to 40 cubic light-years of empty space. If you could stand outside the Milky Way and look at it with eyes that could resolve individual stars, you would see mostly darkness punctuated by scattered points of light. Like a handful of fireflies released into a football stadium at night, the stadium is real, the fireflies are real, but the defining characteristic of the scene is the darkness between them, not the specks of light within it. The habitable zone around our Sun, the orbital band where temperatures permit liquid water on a rocky planet's surface, spans a narrow ring between roughly 0.95 and 1.7 astronomical units from the Sun. That ring is roughly 70 million miles wide. It sounds substantial, until you hold it up against cosmic distances. Compared to the 4 light-year gulf to the next star, the habitable zone occupies less than 1/trillionth of 1% of the distance between neighbours. The warm zone around each star is a microscopic dot embedded in a cold void that extends for trillions of miles in every direction. Earth sits within that dot. Every living thing that has ever existed on this planet depends on its continued placement within that dot. Now, zoom out further, far beyond the scale of individual stars and their neighbourhoods. The universe reveals its large-scale thermal architecture, and the picture becomes even more lopsided. Galaxies are not distributed evenly through space. They cluster along vast filaments and walls, shaped by gravity acting on the density variations seeded in the first moments after the Big Bang. Between these filaments stretch cosmic voids, enormous regions of space containing almost no galaxies at all. These voids are the dominant feature of the universe's large-scale structure. A typical cosmic void spans 100 to 300 million light-years across. The largest known voids exceed 1 billion light-years in diameter. Scientists estimate that cosmic voids occupy approximately 80 to 90% of the total volume of the observable universe. The filaments, walls, clusters, and galaxies where stars actually burn crowd into the remaining 10 to 20%. This means that if you selected a random point anywhere in the observable universe, the overwhelming probability is that you would find yourself in a void, far from any galaxy, far from any star, surrounded by nothing but the 2.7 Kelvin glow of the cosmic microwave background stretching to the horizon in every direction. You would be floating in a region of space colder than almost anything on Earth, darker than any night sky visible from our planet's surface, emptier than the best vacuum chamber ever constructed by human hands. Even within the filaments where galaxies concentrate, most of the volume remains cold. Galaxies themselves are mostly empty space. The Milky Way's stellar disk is thin and sparse. Stars occupy an infinitesimally small fraction of galactic volume. Walk a straight line through the Milky Way in any random direction, and you would pass through light years of near vacuum for every fraction of a second you spent inside the atmosphere of a star. The numbers, when assembled together, paint a portrait of a universe that is overwhelmingly cold. The observable universe has a radius of approximately 46.5 billion light-years. Its total volume is roughly 4.2 times 10 to the 80th cubic meters. The total volume of all stars in the observable universe comes to approximately 10 to the 51st cubic meters. Divide stellar volume by total cosmic volume, and you get a fraction on the order of 10 to the negative 29th. That means the hot interiors of stars occupy less than 1 billionth of 1 billionth of 1 billionth of the total volume of space. The rest is vacuum at or near the cosmic microwave background temperature. The intergalactic medium offers an interesting complication to this picture. Between galaxy clusters, thin strands of gas thread through the cosmic web along filaments. Some of this gas is surprisingly hot, reaching temperatures of 100,000 to 10 million Kelvin, where gravitational shocks have heated it during the process of structure formation. But the word hot here is misleading in a thermal sense. The temperature of a gas measures the average kinetic energy of its particles. A gas can have a very high temperature while simultaneously having an extremely low density. High temperature and low density together mean very little thermal energy per unit volume. The intergalactic medium may be technically hot in terms of particle velocity, but it is so sparse that a cubic meter of this material contains only a handful of particles. Standing inside it, you would feel nothing, no warmth whatsoever. It would be indistinguishable from hard vacuum for any practical thermal purpose. This distinction between temperature and thermal energy is essential for understanding why the universe is cold despite containing hot things. Temperature is an intensive property. It describes the state of whatever matter is present. Thermal energy is an extensive property. It depends on how much matter exists at that temperature. A single particle moving at a velocity corresponding to 1 million degrees carries an almost unmeasurably tiny amount of actual energy. A room full of air at 20 degrees Celsius contains astronomically more thermal energy than a cubic light year of intergalactic plasma at 10 million degrees. The intergalactic medium is hot in name only. In practice, it contributes nothing meaningful to the thermal environment of anything passing through it. The cold vacuum wins not because it is powerful, but because it is everywhere. It does not need to defeat warmth. It merely needs to exist in vastly greater quantity. And it does, by a margin so extreme that all the heat in all the stars, in all the galaxies, amounts to a rounding error in the thermal ledger of the cosmos. The universe is not a place where hot and cold compete on roughly equal terms. It is a place where cold has already won, totally and completely, across essentially all of space and most of time. The cosmic web illustrates this imbalance with striking clarity. Maps of the large-scale distribution of galaxies, assembled from surveys like the Sloan Digital Sky Survey, reveal a structure that resembles foam. Thin, bright walls and filaments surround enormous dark voids. The bright parts, where galaxies and galaxy clusters trace out the scaffolding of the web, occupy a thin minority of the total volume. The dark parts, the voids, dominate overwhelmingly. Looking at these maps, you see a universe where structure is the exception and emptiness is the rule. Filaments are cobwebs strung across cathedral-sized spaces of darkness. Inside those voids, the temperature story is simple and absolute. Nothing heats the void except the cosmic microwave background. No stars burn there in meaningful numbers. No accretion disks rage. No stellar nurseries glow. The void sits at 2.7 Kelvin. Decade after decade, century after century, eon after eon, unchanging and undisturbed across timescales that make the age of the Earth look like a heartbeat. The cold in these regions is not the temporary cold of a winter night that will end when the sun rises. It is not seasonal. It is not cyclical. It is the permanent cold of a universe whose original heat has been stretched and diluted beyond recovery. This is the thermal reality of the universe laid bare. The hot objects that dominate our experience, that fill our sky with light, that sustain life on Earth, account for a share of cosmic volume so negligibly small that rounding it to zero would introduce less error than the uncertainty in our measurements of almost any other cosmological quantity. Now it is time to say what that truth actually means. Not just for physics, not just for astronomy, but for our understanding of where we fit in the cosmos and what kind of universe we actually inhabit. We live in a thermal outlier, a statistical anomaly, a pocket of warmth so improbable against the backdrop of cosmic cold that its existence demands not just explanation, but something approaching careful attention. Consider what is required for Earth to be warm. Start with the obvious. We need a star. Not just any star. A star of the right mass burning at the right rate, emitting the right spectrum of radiation to heat a rocky planet without sterilizing it. The Sun delivers this with remarkable precision. Its luminosity has remained stable enough over 4.5 billion years to permit the slow, patient accumulation of biological complexity on at least one orbiting world. A star 10% more massive would burn hotter and die sooner, possibly before complex life had time to evolve. A star 20% less massive would emit most of its energy as infrared radiation, changing the chemistry of any atmosphere warmed by it. Earth must also orbit at precisely the right distance. A few percent closer and the oceans evaporate. A few percent farther and they freeze. This habitable zone, the orbital sweet spot where liquid water can persist on a rocky surface is so narrow relative to the solar system that it occupies less volume than the gap between Jupiter and Saturn. Even within the habitable zone, distance from the star is not enough. Earth requires an atmosphere. Without one, the surface would swing between brutal extremes with every rotation, baking under direct sunlight and freezing in shadow, just as the moon does. Earth's atmosphere performs a service so fundamental it is easy to overlook. It traps infrared radiation through the greenhouse effect, redistributes heat from the equator to the poles through convection, and moderates temperature swings between day and night. Without the atmosphere, Earth's average surface temperature would hover around -18 degrees Celsius, cold enough to freeze the ocean solid. The greenhouse effect, driven primarily by water vapor and carbon dioxide, raises the average to approximately 15 degrees Celsius. A swing of 33 degrees that makes the difference between a frozen rock and a living world. The atmosphere itself is a product of planetary history so specific that small changes at any point could have produced a completely different outcome. Earth's mass had to be large enough to gravitationally retain a substantial atmosphere against the erosion of solar wind, but not so large that it accumulated a thick hydrogen-helium envelope like Jupiter. Earth's magnetic field, generated by convection currents in a liquid iron core, had to be strong enough to deflect charged particles from the Sun that would otherwise strip the atmosphere away over geological time. Mars likely lost much of its atmosphere through exactly this process. Its magnetic field faded as its core cooled, leaving the solar wind to slowly erode its protective blanket of gas. Mars was probably warm once. It is not warm now. Layer these requirements together, and a picture emerges of how many conditions must align simultaneously for a planet to maintain warmth over geological time. The right star, the right orbit, the right mass, the right atmosphere, the right magnetic field, the right geological activity to cycle carbon and regulate surface temperature over billions of years, the right amount of water, the right kind of moon to stabilize axial tilt and prevent catastrophic climate oscillations, and possibly even the right placement of large outer planets to deflect incoming comets and asteroids with sterilizing frequency. Each requirement is itself the product of a chain of physical events stretching back to the formation of the solar system, back through the supernova explosion that seeded the molecular cloud that birthed the Sun with heavy elements, back through the stellar generations that preceded our Sun, back to the galaxy formation process, back to the density fluctuations in the early universe that seeded the galaxy in the first place. The chain extends across the entire history of cosmic evolution. Pull any single link out and the rest collapses. The warmth you feel on your skin right now is the end product of that chain, stretching backward through 4 billion years of planetary history, 5 billion years of stellar evolution, and 13.8 billion years of cosmic expansion. None of it was guaranteed. The chain did not have to produce this result. Scale this perspective outward. Earth is one warm world orbiting one stable star in one spiral arm of one galaxy among trillions. Our galaxy contains an estimated 200 to 400 billion stars. Missions like Kepler and the Transiting Exoplanet Survey satellite have confirmed thousands of exoplanets, and the Kepler mission alone suggested that roughly 1 in 5 Sun-like stars may host a rocky planet in the habitable zone. That extrapolation would yield billions of candidates in the Milky Way alone, but confirming that a planet sits in the habitable zone is not the same as confirming it is warm in the way Earth is warm. Orbital distance is only the first filter. A planet can occupy the correct orbital distance and still be a frozen wasteland if it lacks an atmosphere, or a scorching hellscape if its atmosphere traps too much heat, or a barren rock battered by radiation if it has no magnetic field to protect whatever atmosphere it managed to accumulate. The number of truly Earth-like worlds, Planets where the surface temperature hovers within the narrow range that permits liquid water, complex organic chemistry, and biological evolution over billions of years may be vanishingly small, or it may be moderately common. We simply do not have enough data to distinguish between these possibilities with confidence. The James Webb Space Telescope is beginning to analyze exoplanet atmospheres, searching for chemical signatures that might indicate habitable conditions. Within the coming decades, we may have our first direct evidence of whether any nearby worlds are warm in the way that matters. The observable universe contains roughly 2 trillion galaxies. Each one harbors its own population of stars, its own scattering of planetary systems, its own vanishingly thin habitable zones surrounding isolated stellar furnaces. The total number of potentially warm habitable worlds across all observable galaxies might reach into the tens of billions, a number so large it sounds hopeful until you remember the denominator. The total volume of the observable universe is approximately 4.2 times 10 to the 80th cubic meters. The combined volume of every habitable zone around every star in every galaxy is a fraction so small that even scientific notation struggles to convey its insignificance. The universe is, in the most literal physical sense, a machine for producing cold, not because it was designed to be cold. There is no intent, no plan, no purpose behind the thermal emptiness. It simply follows physical laws that, when applied to the actual distribution of matter and energy across cosmic volumes and cosmic timescales, inevitably produce a cosmos where warmth is the exception and cold is everything else. The laws of thermodynamics mandate that isolated systems evolve toward maximum entropy, toward the most probable distribution of energy, which is a uniform, featureless, cold equilibrium. Stars resist this trend locally by converting gravitational potential energy into thermal radiation, but they accelerate it globally by radiating that energy into the ever-expanding void where it dilutes and cools. Every star that shines is hastening the universe toward its final thermal state. The very process that creates warmth locally contributes to the ultimate triumph of cold universally. Stars are afterthoughts, thermally speaking. Brilliant, essential for the existence of anyone capable of asking about cosmic temperatures, but afterthoughts nonetheless. The main product of cosmic evolution is empty, cold, silent vacuum. Stars and their warm zones are a side effect. A glorious one, but a side effect. This perspective gains a new dimension when you consider time as well as space. The universe has existed for 13.8 billion years. Stars have been burning for roughly 13.5 billion of those years since the first generation ignited from primordial hydrogen a few 100 million years after the Big Bang. But stars will not burn forever. The supply of hydrogen available for nuclear fusion is finite. It is being consumed in stellar cores across every galaxy and will never be replenished by any known physical process. The timeline of stellar extinction stretches across an almost incomprehensible future. New stars ignite every year in the Milky Way alone, roughly 3 solar masses worth of new stellar material collapsing and catching fire annually. But the rate of star formation has been declining since its peak roughly 10 billion years ago. The universe is past its prime. The golden age of stellar ignition is behind us. Each passing billion years sees fewer new stars born than the billion years before. Red dwarfs, the most frugal stellar consumers, will persist long after every other type of star has died. The most miserly red dwarfs will burn steadily for perhaps 10 to 15 trillion years before exhausting their supply. That is roughly 1,000 times the current age of the universe. After the last red dwarf sputters out, no new stars will ignite. The raw material will have been consumed or dispersed beyond recovery. The universe will enter what physicists call the degenerate era, a period dominated by the cooling remnants of dead stars. White dwarfs, the compressed cores left behind when stars like our Sun exhaust their fuel will cool slowly over trillions of years. They begin their afterlives glowing intensely with residual heat, some initially hotter than the surfaces of the most massive living stars, but they produce no new energy. They are embers, not fires. Over time scales measured in quadrillions of years, they will fade from dim yellow to deep red to infrared to microwave, and finally to an equilibrium temperature indistinguishable from the cosmic background. Black holes will dominate the mass budget of the far future cosmos, slowly evaporating through Hawking radiation over timescales that make the stellar era look like the flash of a camera. A stellar mass black hole takes roughly 10 to the 67th years to evaporate completely. A supermassive black hole at the center of a galaxy requires roughly 10 to the 100th years. When the final black hole evaporates in a faint burst of radiation, the universe will contain nothing but diffuse particles and photons, drifting apart in an expanding void that grows colder with every passing moment. When measured against this cosmic timeline, the era of starlight is a brief flicker. The period during which stars exist and shine spans roughly 100 trillion years at most. That sounds like an eternity, and it is by human standards. But the eras that follow, the long cooling of white dwarfs, the slow evaporation of black holes, the infinite expansion of cold, empty space, extend across timescales so much longer that the stellar era shrinks to a rounding error. If you represented the entire future history of the universe as a single year, with the Big Bang on January 1st and the evaporation of the last black hole on December 31st, the entire era of starlight, all 100 trillion years of it, would occupy the first fraction of a millionth of a second after midnight on January 1st. The rest of the year, every month, every week, every day, every hour, every remaining second, would pass in total darkness at temperatures approaching absolute zero. The age of warmth is not just brief. It is so brief compared to the cold future that calling it brief is itself an understatement. The universe will spend the overwhelming majority of its existence in total darkness and total cold. Stars are a temporary phenomenon. The warmth they provide is a temporary gift. The habitable zones they create are temporary shelters against an eternal cold that will eventually reclaim everything. Every living thing that has ever existed on Earth or on any other world in any galaxy exists during this narrow window when the universe still produces light and heat. Before the first stars, there was only cooling radiation approaching the background temperature. After the last stars, there will be only cooling remnants fading toward absolute zero across timescales, so long they make the current age of the universe seem like the blink of an eye. The warm present is sandwiched between a cold past and a colder future. Earth itself is temporary. The Sun has roughly 5 billion years of stable hydrogen burning remaining. After that, it will swell into a red giant, expanding its outer layers past the orbit of Venus, and possibly engulfing Earth entirely. Long before that dramatic endgame, the Sun's gradually increasing luminosity will render Earth uninhabitable through a subtler mechanism. Stars like the Sun grow slowly brighter over their main sequence lifetime, as hydrogen fusion gradually changes the chemical composition of the core. In roughly 1 billion years, solar output will have increased by approximately 10%, enough to trigger a runaway greenhouse effect that boils the oceans and bakes the surface. Life on Earth's surface will become impossible. The warmth that has sustained biology for 4 billion years will become the heat that destroys it. Even the Sun's gift of warmth comes with an expiration date printed in the physics of stellar evolution. Against this background of cosmic cold and temporal finitude, the existence of warmth on Earth takes on a weight that numbers alone cannot fully convey. We are not merely warm. We are warm in a universe that overwhelmingly is not. We are warm during a cosmic era that will not last. We are warm on a planet whose warmth depends on a chain of physical conditions so specific and so fragile that changing any one of them would break the chain entirely. The warmth is not guaranteed. It is not permanent. It is not the natural state of things. It is a gift from a particular star at a particular distance during a particular epoch of cosmic history, and it will be withdrawn. Every sunrise is an act of thermal defiance against the cosmic default. Every ocean that remains liquid is a local exception to conditions that would freeze it solid anywhere else in the observable universe beyond the narrow orbital band it happens to occupy. Every living cell that maintains its internal temperature through metabolism is participating in a contest against the cold that the cold will eventually win. The second law of thermodynamics guarantees that energy spreads from concentrated to diffuse, from hot to cold, from ordered to disordered. Stars concentrate energy temporarily by fusing hydrogen under gravitational pressure. Life concentrates energy temporarily by building complex molecules from simple ones, but both processes are local and temporary reversals of a universal trend. The trend points toward equilibrium, and equilibrium at cosmic scales means cold. It means the background temperature. It means 2.7 Kelvin, and eventually even less than that. The universe does not need to fight warmth. It merely needs to wait. Time is on its side. The stars will burn out. The warm places will cool. The cosmic microwave background will fade toward zero, and the cold will be all that remains, stretching across every direction and every distance for a duration that has no meaningful end. What remains scientifically open is how warmth came to exist at all against such overwhelming odds, and what its existence implies. Physicists are still working to understand why the fundamental constants of nature, the strength of gravity, the mass of particles, the speed of light, happen to take values that permit stars to form, atoms to be stable, and complex chemistry to emerge. Slight changes to any of these constants would produce a universe too hot, too cold, too short-lived, or too structureless for anything resembling life to develop. Whether this fine-tuning reflects some deeper physical principle, or whether it is simply a feature of the universe we happen to inhabit from among a vast landscape of possible universes with different constants, remains one of the deepest unsolved questions in all of physics. Research with the James Webb Space Telescope continues to push the boundaries of what we know about the early universe, examining the first galaxies to form after the Big Bang, probing the atmospheric chemistry of distant exoplanets, and testing our models of cosmic structure formation against the sharpest observations ever made. Future missions may determine whether any nearby worlds harbour the atmospheric signatures associated with biological activity, giving us, for the first time, data about whether warmth of the kind that produces living observers exists anywhere beyond Earth. The cosmic microwave background itself still holds information yet to be fully extracted. Future measurements of its polarization, the orientation of the electromagnetic waves, rather than just their temperature, may reveal imprints left by gravitational waves from the inflationary epoch, opening a window onto the physics of the first fraction of a second after the Big Bang at energies far beyond anything a particle accelerator could achieve. The faint cold glow that fills the universe still has secrets to give up, and the question of the universe's ultimate fate, whether expansion continues forever, whether the mysterious dark energy that drives that expansion remains constant or strengthens over time, whether there is some mechanism by which new structure could eventually form even in the deep cold future, these questions remain genuinely open. The physics of the far future is uncertain in ways that our current theories cannot resolve. What we do know is that the universe follows laws. Those laws drive it toward cold, and the warmth we experience right now, the narrow band of temperature that allows water to remain liquid and chemistry to build complexity and neurons to fire, with the electrochemistry that produces thought, exists in a universe that almost entirely lacks these conditions. The title of this story promised a terrifying truth. Here it is, stated as plainly as the physics allows. The universe is cold, not in some limited, local, temporary way. Cold in the most total, permanent, and all-encompassing way that the word can carry. 2.7 Kelvin across billions of light-years of void, near absolute zero in every direction you could ever travel beyond the thin shell of warmth surrounding your local star. The hot objects are spectacular and real, but they occupy a fraction of cosmic volume so negligibly small that rounding it to zero would not meaningfully change any calculation in cosmology. The warm places where liquid water flows and chemistry builds and life thinks and wonders are rarer still, nested inside the already rare shells of stellar warmth, dependent on planetary conditions that must align with extraordinary precision. The terrifying truth about how cold space really is comes down not to the number, but to the proportion. It is the realization that warmth, the condition you take for granted every moment of every day, the condition that makes you possible, exists in an almost immeasurably small fraction of all that is. The cold is not surrounding us the way darkness surrounds a campfire, with the fire holding its own against the night. The cold is the night. It is everything. And our warmth, the warmth of Earth, the warmth of life, the warmth of consciousness contemplating its own improbability, is a single candle burning in a darkness that stretches farther than light has travelled since the beginning of time. That candle is real. Its flame is genuine. The warmth it provides has lasted 4 billion years and sustained every living thing that has ever drawn breath or turned toward the sun. But the darkness around it is bigger than any mind can hold, bigger than any telescope can see, bigger than any number can capture. Look up tonight. See the stars. Know what they are. Each one is a furnace fighting the same cold that presses in from every direction. Each one warms a tiny sphere of space around itself, creating a brief local exception to the universal rule. Some of those stars may warm worlds where other minds look up at other skies and wonder about the cold between the lights. We cannot know, but we can know this. The warmth is here now, on this world, in this moment. It is extraordinary, it is temporary, and it is ours. To fully appreciate the significance of the 2.7 Kelvin flaw, it helps to trace the history of how physicists came to understand absolute zero itself and why it represents not just a very cold temperature, but a fundamental boundary of physical reality. The concept of absolute zero grew out of centuries of careful study of how gases behave under different thermal conditions. In the 17th and 18th centuries, scientists like Robert Boyle and Jacques Charles documented the relationships between the pressure, volume, and temperature of gases. What they found, when the data was analysed carefully, was that all gases seemed to converge on the same volume, essentially zero, at the same extreme low temperature. When the early experimental data was extrapolated, the answer pointed to approximately negative 273 degrees Celsius. This was the temperature at which the molecules of a gas would theoretically stop moving entirely, the temperature at which all thermal motion ceased. The precise theoretical basis for this limit was later established through thermodynamics. The first law of thermodynamics states that energy is conserved. It cannot be created or destroyed, only converted from one form to another. The second law states that in any closed system, entropy, the measure of disorder, tends to increase over time. Energy spontaneously flows from hot to cold, not from cold to hot. These two laws together define the direction of thermal processes throughout the universe. They are not approximations or conventions. They are among the most thoroughly tested and most robust principles in all of science. No known exception to either law has ever been confirmed. The third law of thermodynamics, formulated in the early 20th century, adds a crucial constraint. It states that the entropy of a perfect crystal at absolute zero is exactly zero, meaning there is no residual disorder, no residual uncertainty about the microscopic state of the system. This seems like a technical detail, but it has a profound consequence. To reach absolute zero, you would need to remove every last bit of entropy from a system, which requires an infinite number of steps. Reaching absolute zero exactly is therefore not merely difficult, it is physically impossible. The third law ensures that absolute zero remains forever just out of reach, a limit you can approach but never achieve. In practice, the coldest temperatures ever achieved on Earth have been reached in laboratories using a combination of techniques. Laser cooling exploits the momentum of photons to slow atoms down, reducing their kinetic energy and therefore their temperature. Evaporative cooling allows the fastest and hottest atoms to escape from a trap, leaving behind a colder population. Magnetic traps hold clouds of atoms in place while these cooling processes occur. Through these methods, physicists have cooled samples of atoms to temperatures measured in billionths of a Kelvin above absolute zero, creating states of matter that have no analogue anywhere in nature, including exotic phases called Bose-Einstein, condensates where quantum mechanical effects become dominant at macroscopic scales. But all of these achievements require continuous active intervention to maintain. The moment the cooling apparatus is switched off, the atoms warm back up toward equilibrium with their surroundings. Sustaining ultra-low temperatures in a laboratory is an ongoing battle against the thermal environment. In the natural universe, beyond any laboratory, the thermal environment is the cosmic microwave background, and that sets the floor at 2.7 Kelvin. This means that the extraordinary work physicists do to approach absolute zero in the laboratory amounts to a fight against a universe that will not let them go below 2.7 Kelvin by natural means. They are working against the grain of cosmic thermodynamics. The universe insists on its baseline temperature with the authority of physical law. What makes the cosmic microwave background so significant is not just its temperature, but its extraordinary uniformity. When you measure the background radiation arriving from opposite sides of the sky, from directions that are separated by hundreds of millions of light years, you find that the temperature is the same to roughly 1 part in 100,000. This uniformity is so extreme that it puzzled physicists for decades. How could regions so far apart, regions that had been separated since the earliest moments of the universe and had never had time to exchange heat, end up at precisely the same temperature? The answer, as mentioned earlier, involves cosmic inflation. During the first tiny fraction of a second after the Big Bang, the universe underwent a period of exponentially rapid expansion. In roughly 10 to the negative 36 seconds, space expanded by a factor of at least 10 to the 26th power. Regions that had been in thermal contact, close enough to exchange energy and reach the same temperature, were suddenly flung far apart by this inflationary expansion. By the time the cosmic microwave background was released, those regions had been separated by distances too vast for light to cross, but they retained the thermal uniformity they had established before inflation tore them apart. Inflation also explains the origin of the tiny fluctuations in the background radiation. During the inflationary epoch, quantum mechanical fluctuations, the inherent randomness of energy at subatomic scales, created microscopic variations in density. Inflation stretched these quantum scale ripples to cosmic dimensions. What started as uncertainties smaller than an atom became density variations spanning millions of light years. Those density variations seeded the formation of all cosmic structure. Every galaxy, every star, every planet, every living thing is the consequence of quantum fluctuations that occurred during the first fraction of a second of cosmic history. and were then stretched to astronomical scales by inflation. The fine-grained temperature map of the cosmic microwave background is therefore not just a picture of the early universe. It is a map of the quantum mechanical origin of all structure. The precision with which the Planck satellite measured these fluctuations has allowed cosmologists to test models of inflation with unprecedented rigor. The observed patterns of temperature variations match theoretical predictions with striking accuracy, providing indirect evidence that inflation actually occurred. The detailed shape of the power spectrum, the mathematical description of how fluctuation strength varies with angular scale, encodes information about the physics of inflation at energy scales far beyond anything achievable in any particle accelerator. In this sense, the coldest, faintest glow in the universe is simultaneously our best observational probe of the hottest and most energetic moments in cosmic history. One of the most counterintuitive discoveries to emerge from precision measurements of the cosmic microwave background concerns the composition of the universe itself. The pattern of temperature fluctuations encodes information about how much ordinary matter, dark matter, and dark energy the universe contains. By matching the observed fluctuation pattern to theoretical predictions, cosmologists have established that the universe we can see and touch, the atoms that make up stars, planets, and living organisms, constitutes only about 5% of the total energy content of the cosmos. Dark matter, a form of matter that does not emit, absorb, or reflect light, but does exert gravitational influence, accounts for roughly 27%. Its existence is inferred from the way galaxies rotate, from the way light bends around massive galaxy clusters, and from the temperature fluctuations in the cosmic microwave background. No one knows what dark matter is made of. The leading candidates are hypothetical particles that interact with ordinary matter only through gravity and the weak nuclear force. Despite decades of searching with underground detectors, particle colliders, and space-based observatories, dark matter particles have never been directly detected. Dark energy, accounting for the remaining 68% of the cosmic energy budget, is even more mysterious. It is the name physicists give to whatever is causing the expansion of the universe to accelerate. Einstein's equations of general relativity allow for a term called the cosmological constant, a form of energy intrinsic to empty space itself that would cause accelerating expansion. The observed acceleration matches what this cosmological constant would predict. But no one understands why empty space should have energy at all, or why it should have precisely the amount observed rather than some other value. The smallness of the cosmological constant, when compared to what naive quantum mechanical calculations would predict, is one of the biggest unsolved problems in theoretical physics. Dark energy has profound implications for the ultimate fate of the universe, and therefore for the ultimate fate of its temperature. If dark energy remains constant, the universe will continue to expand at an accelerating rate forever. Galaxies will drift further and further apart. Eventually, galaxies beyond a certain distance will be receding from us faster than light, making them permanently inaccessible. The observable universe will shrink. The cosmic microwave background will cool. Stars will exhaust their fuel and die. The temperature of the universe will approach absolute zero more and more closely as expansion continues, though it will never quite reach it. If dark energy were to strengthen over time, the fate could be more dramatic. A growing dark energy term could eventually tear apart not just galaxies, but individual atoms, in an event called the Big Rip, though current observations give no strong indication this will occur. If dark energy were to weaken or reverse, gravity could eventually halt the expansion and cause the universe to collapse back on itself in a big crunch, with temperatures rising catastrophically as everything compressed again toward the conditions of the Big Bang. Current evidence strongly favors continued accelerating expansion, and therefore continued cooling, but the nature of dark energy remains sufficiently uncertain that these alternatives cannot be entirely ruled out. What is clear is that the interplay between thermal physics and cosmic expansion determines not just what the universe is like today, but what it will become. The temperature of the cosmic background is not merely a measurement of current conditions. It is a tracer of cosmic history and a predictor of cosmic destiny. Every degree it falls marks another step in the irreversible cooling that began at the Big Bang and will continue until the last remnants of stars fade to equilibrium with an expanding void. The science of cosmic temperatures also connects intimately with biology. Life, as far as we currently know it, requires liquid water. Water is liquid between 0 and 100 degrees Celsius at standard atmospheric pressure. This is an extraordinarily narrow range when placed in the context of the temperature scales at play in the universe. The surface of the Sun sits at 5,500 degrees Celsius. The core of the Sun sits at 15 million degrees Celsius. The cosmic background sits at approximately negative 270.45 degrees Celsius. The habitable range for liquid water, the range in which Earth's average surface temperature falls, is a narrow band barely visible between these extremes. Life also requires chemical reactions. Chemistry depends on atoms forming and breaking bonds with one another, a process that requires a certain minimum temperature to proceed at a biologically useful pace, but cannot survive temperatures so high that complex molecules are torn apart. The biochemistry of known life, built around carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, operates within a range of roughly 0 to about 120 degrees Celsius. This range is not arbitrary. It reflects the stability ranges of the chemical bonds that biological molecules depend on. At colder temperatures, chemical reactions slow dramatically. At hotter temperatures, the bonds holding large biological molecules together begin to break. Some organisms, called extremophiles, have evolved to tolerate conditions far beyond what most life can survive. Thermophilic bacteria thrive in hot springs at temperatures approaching 100 degrees Celsius. Psychrophilic organisms have been found active in Antarctic ice at temperatures below negative 20 degrees Celsius. Certain microbes survive in highly acidic or highly alkaline environments, in high radiation environments, in environments with no oxygen. The range of conditions under which life of some form can persist on Earth is wider than was once believed. But even the most resilient extremophile depends on liquid water, on the availability of chemical energy, and on protection from radiation intense enough to destroy the molecular machinery of cells. The existence of these organisms does not change the fundamental constraints. It simply demonstrates that life can exploit a wider range of conditions within those constraints than naive assumptions would suggest. A world that is perpetually below the freezing point of water, or above the temperature at which complex organic molecules decompose, remains off limits to the kind of chemistry that powers every living thing on Earth. Whether other forms of chemistry could in principle support what we might call life under radically different conditions, whether hypothetical organisms could exploit non-water-based solvents or operate at temperatures far outside Earth's habitable range, remains genuinely open. Some theoretical proposals suggest that liquid methane or liquid ammonia could in principle serve as solvents for alternative biochemistries. Saturn's moon Titan has a thick nitrogen atmosphere and lakes of liquid methane on its surface at temperatures around negative 179 degrees Celsius. Whether anything actually lives there is unknown. No mission has yet searched for life in Titan's liquid methane lakes. But even granting the possibility of radically different biochemistries, the thermal constraints on any form of complex chemical information processing remain severe. Chemistry requires atoms. Atoms require nuclear stability. Temperatures high enough to disrupt atomic structure temperatures exceeding tens of thousands of degrees would prevent the formation of any complex molecules, regardless of what chemistry they were based on. At the other extreme, temperatures approaching absolute zero cause chemical reactions to proceed with extreme slowness, making it hard to imagine how any process requiring the organized exchange of chemical information could proceed at a useful rate. The universe is cold, nearly all of it, nearly all of the time, and the warmth that makes chemistry fast enough and stable enough to support biology exists in the thinnest possible slice of cosmic space and cosmic time. The research agenda for the coming decades is, among other things, an attempt to measure how thin that slice really is. Understanding the exact fraction of planets in the habitable zones of stable stars that actually develop habitable surface conditions will require generations of telescope observations. Understanding whether any of those planets host life will require detecting biosignatures in their atmospheres, chemical signals like the combination of oxygen, methane, and water vapor that, if found together, would strongly suggest biological activity. Understanding whether complex life capable of building civilizations and asking questions about cosmic temperatures is common or rare across the universe may ultimately be unanswerable, at least on timescales accessible to human civilization. What can be said with confidence is that the universe does not make warmth easy. It does not make life easy. The physical conditions required for complex chemistry to sustain itself over geological time are demanding, specific, and dependent on a chain of circumstances that extends from the quantum fluctuations of the earliest moments of cosmic history to the precise orbital distance of a rocky planet around a stable star. The cosmic default is cold. Warmth is the deviation, and every form of inquiry that tries to understand why that deviation exists where it does is, at some level, asking the same question that the sight of a night sky has always provoked. Why are we here in this warm place, looking out at all that cold? The answer, insofar as physics can provide one, is that the cold came first. That warmth emerged from it briefly, locally, improbably. That stars converted the universe's initial thermal inheritance into structured energy long enough for planets to form around them, and for chemistry on at least one of those planets to cross the threshold into self-replicating complexity. That everything capable of noticing the temperature of the universe is itself a product of the narrow window in which warmth and structure coexist. The cold is not the enemy of life. It is the context in which life, improbably and briefly, appeared. Understanding the depth of that cold, the permanence of it, the completeness of it across cosmic scales, is not a reason for despair. It is an invitation to appreciate the extraordinary specificity of the conditions that made us possible, and to continue the scientific work of understanding how rare or common that specificity might be across the rest of the vast, quiet, cold universe. There is one more dimension of the cold universe worth examining carefully before we close, and that is what happens at the smallest scales of physics, down where quantum mechanics governs the behavior of matter and energy. At the atomic and subatomic level, the concept of temperature takes on an even more nuanced character. Quantum mechanics describes a world where particles do not have precise positions or momenta simultaneously, where the act of measurement disturbs the system being measured, and where the lowest possible energy state of any system, the quantum ground state, is not zero, but some small positive value called the 0-point energy. Even at absolute zero, if you could somehow reach it, quantum mechanical systems would still possess this residual energy. They would not be entirely still. They would vibrate with the minimum possible quantum motion. This 0-point energy is not a technicality. It has real observable consequences. It prevents liquid helium from solidifying at atmospheric pressure even at temperatures approaching absolute zero, because the zero-point motion of helium atoms is large enough to keep them from settling into the fixed lattice positions of a solid. You can solidify helium only by applying external pressure to constrain the atoms. It contributes to the Casimir effect, a measurable force that arises between two very closely spaced metal plates in vacuum, caused by the difference in quantum vacuum fluctuations inside and outside the gap. The zero-point energy of quantum fields is real, measurable, and consequential. Some physicists have speculated that the zero-point energy of the quantum vacuum, the irreducible energy that empty space possesses even in its ground state, might be related to dark energy, the mysterious energy driving the accelerating expansion of the universe. But naive calculations of what the vacuum energy should be, based on quantum field theory, give answers that are wildly larger than what is actually observed. The discrepancy is enormous, around 120 orders of magnitude, depending on the cutoff assumed. This has been called the worst prediction in physics, and reconciling theoretical quantum vacuum energy with the observed value of dark energy remains one of the deepest unsolved problems in fundamental physics. The connection between quantum mechanics and the coldness of the universe runs even deeper. The fact that matter exists at all, rather than the universe being a sea of pure radiation, depends on asymmetries in the behavior of matter and antimatter at the quantum level. In the earliest moments after the Big Bang, matter and antimatter were created in equal amounts. For reasons that are not fully understood but are actively researched, matter slightly outnumbered antimatter by about 1 part in a billion. When matter and antimatter annihilated each other, the slight surplus of matter survived. That surviving matter is everything in the universe today. Every star, every planet, every atom in every living organism is part of the tiny residue left over from the mutual annihilation of almost equal amounts of matter and antimatter in the hot early universe. If the quantum asymmetry between matter and antimatter had been slightly different, or zero, the universe would contain only radiation and no matter at all. No atoms would have formed, no stars would have ignited, no planets would orbit anything, no temperature gradients would exist beyond the uniform cooling of the background radiation. The entire thermal landscape of the universe, with its stars and cold voids and rare warm planets, depends on a quantum asymmetry so small it is measured in parts per billion. These connections between the largest and smallest scales of physics, between cosmic temperatures and quantum mechanics, between the thermal history of the universe and the fundamental forces that govern particles, make the question of cosmic cold one of the most richly connected topics in all of science. Answering it fully requires not just astronomy, but particle physics, thermodynamics, chemistry, planetary science, and biology. It is a question that pulls threads from every corner of the scientific enterprise and weaves them together into a picture of extraordinary coherence and depth. The 2.7 Kelvin background temperature is not just a number. It is a convergence point for the history of the universe, the physics of fundamental particles, the dynamics of cosmic expansion, the formation of structure, and the emergence of complexity. Every field of physics touches it in some way, and every attempt to understand it more precisely, through better satellite measurements, through deeper understanding of inflation, through clearer models of cosmic structure formation, advances our grasp of why the universe is the way it is, and how the conditions for warmth and life came to exist within it. That is where the science stands today. The measurements are precise, the theoretical framework is mature, and the deepest questions remain genuinely open. Why do the constants of nature allow warmth to exist? Why did the quantum fluctuations of inflation seed exactly the density variations that would eventually produce galaxies and stars? Why does dark energy have the value it does, small enough to allow structure to form, but large enough to drive accelerating expansion. What is the true frequency of Earth-like warmth across the universe? Is the warm, wet, biologically active planet an extraordinarily rare accident, or a common feature of galaxies everywhere? These questions are not rhetorical. They are research programs, active areas of scientific investigation that are advancing with every new observation, every new experiment, every new theoretical insight. The cold universe is not a closed subject. It is one of the most active frontiers in science, precisely because understanding why warmth exists where it does requires understanding almost everything about how the universe works at every scale. The cold is the context, the warmth is the question, and the scientific pursuit of that question, conducted in the warm, wet, improbable laboratory of a planet orbiting a middle-aged star in a quiet spiral arm of one galaxy among 2 trillion, is itself one of the more remarkable features of a universe that has been cooling, slowly and steadily, for nearly 14 billion years.